For 4-38, there's a steel ball coming out of a furnace at 900 degrees Celsius, and it's being annealed to 100 degrees Celsius. And you're asked to find the time it takes for that process, and then the total heat transfer rate for this amount of steel balls. First, you want to find the corrected length so that you can solve for the BO number, and since the BO number is less than 0.1, we can use the lumped analysis assumption. To do that, you have to find B, and then this is the equation for that assumption, and you just have to rearrange for T. And then to find the heat transfer rate, you have to find the Q for an individual ball and then just multiply that by this rate. And that's what you get. For 4-100, there is wind blowing on the soil, and so we can treat this as convection at the surface, which means we should use case 3 of the semi-infinite solid assumption. And this is the equation for that assumption. But since h is so large, it practically is like h approaching infinity, and so that means the exponential is approaching infinity, which means that we can only focus on this to get an answer. This is the equation to use, and since there's this error function, I just plugged everything into Excel. For 4-115, there is this solid, and we have a plane wall in this direction, one of them, and then 2 plane walls going this way. The blue is a thickness of 4 centimeters, and then we can assume that there's a ghost block under here, and so that the total thickness is 12 centimeters, double the 1 block. And so you just want to find T using the one-term approximation method, which means that tau has to be greater than 0.2. And then this is the equations that I used, just rearranging for everything. And then I just plugged it into Excel. And the first liquid appears at the corners because that's where the maximum exposed surface area is. Okay, and then for this last one, we know the binary diffusion coefficient, and we want to know the penetration depth at 40% the initial concentration. This is the equation that you use, and we can simplify this using terms that we know. And then we know that the left-hand side equals 0.6, and then to find x, you do the inverse of the ERFC function, which is this, and then you just solve for x at the different times that it gives you.